So in our previous video, we talked about the most important definitions of empirical formula and molecular formula. So in this video, we are going to talk about how to do calculations related to empirical and molecular formulas. Now stay with me to the end of the video. We are going to solve about 6 examples to illustrate empirical and molecular formulas. Starting with question number 1. It says the compound of nitrogen and oxygen is analyzed and a sample weighing 1.587 grams is found to contain 0.483 grams nitrogen and 1.104 grams oxygen. What is the empirical formula of the compound? So from this problem, we can see that the mass of nitrogen given to us here is 0.483 grams. And we can see that the mass of oxygen given to us here is about 1.104 grams. So first things first, let us find the empirical formula. Now let's arrange our problem like this. We have nitrogen and we have oxygen. So let's have the masses here, 0.483 grams. Then we have 1.104 grams. So first things first, we are going to divide each of these masses by their atomic masses. So I will say divide by their atomic masses. So let's divide by the atomic masses. I'm going to have that 0.483. I'm dividing by 14. I'm dividing 1.104. I'm going to divide this by 16. What am I going to have? Okay, so we are going to have 0.0345 here. We're going to have 0.069 here. Now we're going to divide through. We're going to divide through by the smallest number here. Divide through by the smallest, by the smaller number. So now we're going to have that the smaller number here is 0.0345. So I'm going to say 0.0345 divided by 0.0345. and 0.069 divided by 0.0345. So what am I going to have? Okay, so this gives me 1 and this gives me 2. Hence, our empirical formula is going to be NO2. Let's solve problem number 2. For the second problem, we are given percentage compositions, and the question goes this way. An analysis of sodium dichromate gives the following mass percentages: 17.5% sodium, 39.7% chromium, and 42.8% oxygen. What is the empirical formula of this compound? So we are going to solve the problem just like this. So we have sodium, Na, we have chromium, Cr, and we have oxygen, O. So these are the 3 elements under consideration. So what is the percentage of sodium given here is 17.5. What is the percentage of chromium? We have 39.7. And what is the percentage of oxygen? We have it at 42.8. Don't forget that these percentages all add up to 100. So if you are given just 2 and you're asked to find the other one, so you simply have to add the 2, subtract from 100 to get the other one. And don't also forget that the percentages you are seeing here can also be referred to as percentage by mass. So we are going to treat these percentage compositions as their masses. So remember the very first step, we are going to convert the masses into moles, and we're going to divide the given masses by their atomic masses. Starting from sodium, so I'm going to say sodium, which is 17.5, I'm going to say 17.5 divided by 23. The atomic mass of sodium is 23. Now I'm going to divide 39.7. I'm going to divide this by 52 because the atomic mass of chromium is 52. And I'm going to divide 42.8 by 16. So this is going to give us 0.761. We're going to have 0.763. And we're going to have 2.675. So we're going to compare the three answers we just got here. Remember, these are the molar amounts of these substances. So the smallest value here is 0.61. So I'm going to divide all through by 0.61, and that gives me 0.761 divided by 0.761, 0.763 divided by 0.761, 2.675 divided by 0.761, and this is going to give us 1.0, 1.0. We're going to have 3.5. Don't forget, at this particular stage, your answers are supposed to be to one decimal place. So 1, 1, and 3.5. So take note of these rules. Anytime you encounter a 0.5 at this point, you're going to multiply through here by 2, because 2 makes a 0.5 to be a whole number. So we're going to multiply everything we have here by 2. What am I trying to say? So I'm going to put a bracket here. I'm going to put a 2 outside. So 2 multiply 1 will give us 2. 2 multiply 1 gives us 2. And 2 multiply 3.5 gives us 7. Hence, the empirical formula of this compound is Na2Cr2O7. Final answer. Take note of these rules. Anytime you encounter, these are special decimals you might want to take into consideration. Anytime you encounter a 0.33 or you encounter a 0.67, it could be a 0.6666 is recurring. That's a 0.67. Now you're going to multiply everything by 3, just like you did here. You multiply by 2. So you're going to multiply by 3 anytime you see these special decimals. Now, why are we multiplying by 3? Don't forget that 1 over 3 is equal to 0.33333. So to make this a whole number, I'm going to be multiplying through by 3, because 3 makes this to be what? A whole number. Now, what about the 0.67? Now, 2 over 3 is equal to 0.66666, which is equivalent to 0.67. So to make this a whole number, I'm going to multiply through by 3. All right. Now, another special decimal you might want to take into consideration is a 0.5. 0.5. We just encountered a 0.5 here. Don't forget that 0.5 is equivalent to saying 1 over 2. 1 over 2 is 0.5. So how can I possibly make 1 over 2 a whole number? Is by multiplying through here by 2. So you can now see the main reason why we multiply this by 2. So anytime you encounter a 0.5 at this point, do well to multiply through by 2. Of problem number 3, very quickly, it says the molecular formula of glucose is C6H12O6. What is the empirical formula? This is a very simple one. So we have to check out the given molecular formula here, which is C6H12 and O6. So these are molecular formula. So we are trying to figure out the empirical formula. Don't forget that the empirical formula is the smallest whole number ratio. So we are going to look for the nearest possible whole number. We can divide all these subscripts here to get the simplest ratio. I'm looking at what we have here. We have 6, 12, and 6. So the simplest number we can divide through is 6. So when 6 divides the 6 here, that gives us 1. When 6 divides the 12, we are going to have 2. and when 6 divides 6, we're going to have 1. So what does that imply? So we are trying to say that 6 over 6 is equal to 1, 12 over 6 is equal to 2, and 6 over 6 is equal to 1. Because the simplest whole number ratio can be gotten by dividing through by 6. So therefore, the empirical formula here is going to be CH2O. So this is the empirical formula for glucose. You can also do it this way. You can say, okay, the numbers I have here include 6, 12, and 6. So how do I reduce these numbers to the smallest possible number? Probably you can start with 2. Let's try 2. So 2, when 2 divides 6, it will give you 3. When 2 divides 12, it will give you 6. And when 2 divides 6, it will give you 3. So we still have another number that can go through here, right? And that number is 3. Let's try 3 this time. Now when 3 divides 3, it's going to give us 1. When 6 divides 3, it's going to give us 2. And when 3 divides 3, it's going to give us 1. So that is how we got 1:2:1. So hence, the empirical formula for glucose is CH2O. We are about to solve problem number 4. Now, problem number 4 is a combustion problem. The question says 3.87 gram sample of ascorbic acid. Ascorbic acid contains only carbon, hydrogen, and oxygen. It gives 5.80 gram CO2 and 1.58 gram H2O on combustion. What is the percentage composition of this compound? And what is the empirical formula? Now, we are going to find the percentage composition of this compound alongside the empirical formula. Don't forget, this is a combustion problem. So first things first, let us isolate the masses given in the problem. So we are given that the mass of the sample of ascorbic acid is 3.87 grams. So you can say mass of sample is given as 3.87 grams. Now, we are also told that this sample was burnt, and during the process of combustion, 5.80 grams CO2 was produced. So I can say mass of CO2 is equal to 5.80 grams. Now, we are also told that 1.58 grams of water was also produced. I can say mass of water produced here is equal to 1.58 grams of water. So what are we going to do from here? So from here, we are going to isolate the masses of carbon, hydrogen, and oxygen, because we've been told that this particular compound, ascorbic acid, is made up of carbon, hydrogen, and oxygen. So first, let us find the mass of carbon in the sample. So mass of carbon in the sample. How do we find the mass of carbon in the sample? Now remember that we have carbon in carbon 4 oxide. So we have to find carbon from this compound here, and we are going to find hydrogen from this compound here. Now let's start by saying that 44 grams of CO2 contains 12 grams of carbon. What does this statement mean? Don't forget that the molecular weight of CO2 is we have 12 plus 16 times 2, that's going to be 32. 32 plus 12 is 44. So in 44 grams of CO2, we have only one atom of carbon, which is equivalent to 12 grams of carbon. So we are trying to do this to find the mass of carbon present in ascorbic acid. So we can say that 44 grams of CO2 contains 12 grams of carbon. So the 5.8 grams of CO2 produced from the combustion is expected to contain how many grams of carbon? So we're going to cross multiply here. 5.80 multiplied by 12 divided by 44. So 5.80 multiplied by 12 divided by 44. Now this is going to give us 1.58 grams of carbon. Okay, it seems I over approximated here, so this is going to give us 1.582 grams of carbon. So that's the mass of carbon in ascorbic acid. Now let us find the mass of hydrogen in ascorbic acid. I'm going to say mass of hydrogen in ascorbic acid. Now don't forget that water, the molecular weight of water is 18 grams. That is 1 times 2 plus 16, that's 18. So that's similar to saying that 18 grams of water contains 1 times 2, which is 2 grams of hydrogen. So in every 18 grams of water, we have 2 grams of hydrogen. So therefore, the 1.58 grams of water produced from the reaction, so 1.58 grams of water produced from the combustion is expected to produce or to contain how many grams of hydrogen? So that is going to be 1.58. I'm cross multiplying, multiplied by 2. And I'm going to be dividing by 18. Now this is going to give me about 0.176 grams of hydrogen. So we have the mass of carbon and we have the mass of hydrogen. What about the mass of oxygen? So in typical combustion reactions like the problem we just solved here, we need to understand that oxygen reacts with fuel, and the fuel here could be a hydrocarbon or an organic compound just like the one we just considered, containing carbon, hydrogen and oxygen. So the oxygen gets incorporated into these products, and this makes it very difficult to measure its original mass directly. So how do we now measure the mass of oxygen? Now, to measure the mass of oxygen, it is very, very important to measure the mass of the products such as CO2 and water, and from there we can now indirectly obtain the mass of oxygen. So the mass of oxygen is often calculated indirectly from the masses of these reactants, namely CO2 and H2O. And let me show you exactly how to do that. So if you want to get the mass of oxygen, you need to first of all take into consideration that the mass of the sample is 3.87, and this sample contains carbon, hydrogen and oxygen. So the mass of carbon plus the mass of hydrogen plus the mass of oxygen, if you add these 3 masses together, it's supposed to give you 3.87. So therefore, if you want to get the exact mass of oxygen, you are going to add up the masses of carbon and the masses of hydrogen and then subtract from the total mass, which is 3.87. Now let's do that together. Let me divide this paper into 2. Let's do that together. So I can say that the mass of oxygen here is going to be 3.87 grams, which is the total mass. Subtract 0.176, that's the mass of hydrogen, minus 1.582 grams, and this is going to give us 2.112 grams of oxygen. So this is the mass of oxygen in ascorbic acid. So we have the 3 masses given to us right here. So now let us now go ahead to calculate for the percentage composition of each of them. So the percentage composition of carbon is going to be, and I'm going to have percentage of carbon, is going to be equal to, now what's the mass of carbon we obtained? That was 1.582. I'm going to divide this by the total mass of the sample, which is 3.87 multiplied by 100. So to get the percentage of hydrogen, I'll do same. So the mass of hydrogen obtained here is 0.176. I'm dividing by the total mass, which is 3.87 multiplied by 100. Same is applicable to oxygen. So the percentage of oxygen is going to be equal to 2.112 divided by 3.87 multiplied by 100. So let's get the answers properly using the calculator. Okay, so the first one gives me about 40.879%. The second one here gives me 4.548. Yeah, 4.548%. Now the last one, so that gives me 54.574%. So these are the percentage compositions of carbon, hydrogen, and oxygen. Now let's head straight to calculating for the empirical formula of ascorbic acid. Okay, so far what have we been able to achieve? We've been able to calculate the mass of carbon to be equal to 1.582 grams, the mass of hydrogen to be equal to 0.176 grams, the mass of oxygen to be equal to 2.112 grams. Then we're also able to calculate for the percentage of carbon, and we got it as that was 40.879%. Then we have the percentage of hydrogen to be about 4.548%. Then we had the percentage of oxygen here to be equivalent to 54.574. So these are the percentage compositions of these elements. Don't forget, there are many other ways to do this. Remember, the time we got the masses of carbon and hydrogen, you can even go straight to find the percentages for carbon and hydrogen, and you add up the two, subtract from 100 to get the other percentage. So there are many ways of doing this. Now let's head straight to the empirical formula for this compound. So I can decide to use the masses here, or I can use the percentages. Now let me use the masses. So I have carbon, I have hydrogen, and I have oxygen. So for carbon, what is the mass of carbon here? We have 1.582. For hydrogen, we have 0.176. We have 2.112. So first things first, divide through by the atomic masses. So I'm going to say I'm dividing this by 12, I'm dividing this by 1, I'm dividing this by 16. So what am I going to obtain from this? So this gives me 0.132. This gives me 0.176. And the last one there, which is 2.112 divided by 16. So that gives me 0.132. Now comparing these three values, which of them is the smallest? We can see that is 0.132. So I'm going to divide through by 0.132, and that gives me 0.132 here, 0.132, 0.132. So this gives me 1. Now let's try the middle value, 0.176. At this point, you have to be very, very careful because of those special decimals I told you about. So 0.176 divided by 0.132. What have you noticed here? I am having 1.33. 1.33. Remember, we talked about a 0.33 decimal appearing at this point. So we have a 0.33 there, and this one gives me 1. So what does that tell you? That implies that I'm going to multiply this through here by, guess what? 3. So I'll put a bracket here, and I'm going to say multiply by 3. So 3 times 1 is 3. 3 times 1.33 is 4. That is 3.99, which is 4, and 3 times 1 is 3. So hence, the empirical formula for this is going to be C6H12O6. Okay, don't forget, we can also obtain the empirical formula by using the percentage compositions. Let's check it out. So I'm giving that carbon, hydrogen, and oxygen. So carbon is equivalent to 40.879, hydrogen is 4.548, and then oxygen here is 54.574. So I'm going to divide through by their atomic mass is 12, 1, and 16. So this one gives me 3.407. This one gives me 4.548, and this one gives me 3.411. If you notice, I'm leaving my answers to 3 decimal places because if your answers are over approximated, you might get the wrong result. So it's very, very important that you don't approximate too much when you're doing things like this. So I prefer leaving my answers to 3 decimal places to avoid errors. So compare the 3 answers you got here. This particular one here is the smallest. So I'm going to divide through by this particular one, and that gives me over 3.407 over 4.548 over, sorry, that's a mistake. I'm dividing this by 3.407 over 3.407. So what are my answers here? I'm going to get 1, I'm going to get 1.33, and I'm going to get 1. So have you noticed the same thing? We got the same exact answers just like when we use the masses. So you can use any of them. You're still going to get the same answers. So therefore, I'm going to multiply through again by 3, like you all know. So 3 multiplied by 1 here is going to give me 3. 3 multiplied by this will give me 4, and 3 multiplied by 1 will give me 3. So therefore, the empirical formula still remains C3H4 and O3. Now let's solve the last problem for this series. This time, we are going to solve a problem that connects empirical formula and molecular formula. We are going to be solving a problem that connects the ascorbic acid we solved previously. Now the question goes this way. It says a sample of ascorbic acid which contains 40.879% carbon, 4.548% hydrogen, and 54.574% oxygen. What is the empirical formula of this sample? The B part of the question says, given that the molecular mass of this compound is 176, what is the molecular formula for this compound? Now let's solve this problem. Now we are going to be ignoring the very first part of the problem that talks about the empirical formula because we just solved this problem in our previous calculation, and we solved it and we got the empirical formula to be C3H4 and O3. So this is the empirical formula for ascorbic acid. Now we are going straight to solve the B part of the question here that says what is the molecular formula. Don't forget that the formula connecting empirical formula to molecular formula is given by, you have empirical formula multiplied by N multiplied by N is equal to molecular formula. Molecular formula. Alright, so empirical formula multiplied by N is equal to molecular formula. What does this mean? Now this N here represents the number of empirical formula units that makes up the molecular formula. Don't forget, if you want to apply this formula here, you are going to be using the molecular mass given in the problem. What am I trying to say? Now this is our empirical formula. So we have that C6H12O6 and O3 here. Now I'm going to be multiplying this whole thing here by N. And I'm going to be equating this to the molecular formula, and that will be the molecular formula mass given to us, and that is equivalent to 176 grams. Alright, so what is the meaning of this? Carbon is 12, so 12 multiplied by 3 gives us 36. So I'm adding 36 to 4, that's 40 plus 40 plus 48, that gives us 88. So I have that 88 multiplied by N, which is 88N, is equal to 176. So let's get the value of our N, dividing both sides by 88. So we're going to have that the value of our N here is equal to 2. What does that mean? That simply means that 2 units of the empirical formula makes up the molecular formula. So meaning that if you add up the empirical formula twice, that gives you the molecular formula. So how do we now get the molecular formula? Now I'm going to be replacing my N value here with 2. And while I'm doing my multiplication, I'm going to be multiplying the subscripts. So since my N now, so I'm going to have that C3H4 and O3. Alright, so put a square bracket here. Now put your 2 outside. Now 2 multiplies 3 to give you 6. So I have C6. 2 multiplies by 4 gives us 8. So I have H8. And 2 multiplies 3 here to give us 6. I have O6. So this is the molecular formula for ascorbic acid. Ascorbic acid. Alright, so this is our final answer. So in my next video, I'm going to be talking about introduction to Lewis structures. See you there.